students, we are looking at electric field strength for the next few days. So you've already read the little theory notes about how electric fields work, what they look like, all of that. So when we look at the electric field strength, that is basically the strength of the electric field at a given point. And the strength we're talking about is the strength that if we were to take a positive test charge, basically a single proton, and put it somewhere within the electric field of a charge, what would the force experienced per unit charge be on that tiny little proton? Okay, so if I were to take a proton and put in, let's say, there, tiny little positive charge, what force would it experience per unit charge? How strong is the electric field at that point? Sorry, excuse the holidays. Okay, how strong is the field at this point? Now, two things to bear in mind here. The first one is that we're talking about the electric field of your main charge, okay? Our little test charge is so small that any electric field that it produces, we consider it negligible. Okay, so we're looking at the electric field produced by the blue charge, not the red charge. It's what's happening to the red charge. And then the second important thing is that this little test charge is positive. Okay, so that is going to affect the direction of our electric field strength. Electric field strength is also a vector, just like force, and the direction of the electric field strength will be affected by this being positive, because let's say the charge producing the electric field is positive. That means that our electric field is going away from our point charge, right? So our direction of our electric field strength for this point charge is away from the charge. But if it were negative, if this charge in the middle were negative, then our electric field would be coming into the charge. So our little point charge would want to move towards that charge. Okay, those are very important things to remember. The sign of your charge is going to affect the direction of the electric field strength, because it will affect the direction that this tiny little proton will want to move in, if it will want to move towards or away from the main charge. Okay, now electric field strength is defined as the force experienced per unit charge, right? Now, I've lost my black cookie, sorry, okay. So electric field strength, firstly, symbol is E, units are newtons per coulomb, okay? And E is defined as the force experienced per unit charge. Now, either we can use this formula, but it's very, very unlikely that you will be given the force. It's much more likely you'll be given the same information as we have been getting. So, for example, the value of the charge on our charged particle, as well as the distance away that we're interested in. Okay, so we need to expand this. Now, we know from Coulomb's law that F equals K, Q1, Q2 over R squared, right? Now, in this case, because we've got one big charge, Q, and one tiny little charge that's basically just a proton, that has the charge of baby Q. So we can change this to be Q of our main charge, and then the charge on our second little point charge, this proton, is baby Q. Okay, so we're going to go and put this in here, and we're going to have that the electric field strength is K, Q, Q, over R squared over Q. Okay, and we can neaten this up a little bit. Remember, when you divide a fraction by a fraction, you're basically going to tip in times. So we're going to change this. E equals K, Q, Q over R squared. We're dividing by Q, so that's the same thing as timesing by 1 over Q, hey? Then we can simplify, our Q's cancel, and we have our main formula, which is that the electric field strength is our proportionality constant multiplied by the charge of the actual main charge emitting the electric field divided by the distance between our point charge and our main charge squared. Okay, so this is our main formula for electric field strength. No, you will very unlikely ever be asked to derive this formula from that one. Okay, you will be given this on your formula sheet, and yeah, it's quite straightforward in terms of how to use it. If you have only one charge, it's nice and easy, but we're going to look at the scenarios where you have two charges and how they're arranged and all of that. For today, we're just looking at if you have one charge emitting an electric field, what the electric field strength might be a certain distance away. Okay. Now, just quickly, from this formula, we can see there is a relationship, right? So we can see that the electric field strength that a charge produces is proportional to the magnitude of the charge, and we can also see that the electric field strength is inversely proportional to the distance squared. So that basically means the higher the charge is on this, the stronger the electric field strength will be, and the further away you go, the weaker the electric field strength will be, which is also just sort of logical. Okay, so I'm going to pause you there. If I've been saying most of the stuff that I've been saying instead of writing it down, it is all written down in your note though. Okay, so I'm going to pause you there and we're going to do some examples. Okay guys, here's our example. We need to determine the electric field strength at X. So we have our charge, it's positive 5 nanocoulombs, and we want to know if I look 30 centimeters away from it, what will the electric field strength be over here at this point? So please read the question carefully. Don't just look at the picture, because if we look at the picture, this looks quite similar to a Coulomb's law question, but it's not. Coulomb's law has to do with force. This has to do with electric field strength, okay, which means we're talking here about E, not about F, okay, and E is equal to KQ over R squared. Now, just like with Coulomb's law, when you substitute in for Q, you ignore the sign, okay? You exclude the sign of your charge. Okay, and just like with Coulomb's law, this is a vector, which means we need to find the magnitude. And to find the magnitude, we use our equation. And we also need to find the direction, because it's a vector, and to find the direction, we use the fact that we know that the electric field strength at X would be in the direction that a positive test charge would want to move, okay, our positive point charge. If I put a positive charge here, because that's positive, it will be away from our charge, to the right. So for direction, you use attraction versus repulsion. Okay, very similar to Coulomb's law, but with this one, your second charge, the charge at X is always positive. Okay, so you're comparing your positive charge with whatever the charge of your main charge is, and our main charge is positive. Okay, so starting off, we need to find the magnitude of our electric field strength by using our equation, and when we sub in for Q, we exclude the charge, the sign of the charge. Okay, so let's go for it. So our electric field strength here is going to equal K, which is 9 times 10 to the 9, times the charge, which is 5 nanocoulombs. So 5 times 10 to the minus 9, over the distance between X and our charge squared, and that distance is in centimeters, so that's 0.3 meters squared. And we solve for electric field strength, and we get 500 nanocoulombs. 500 newtons per coulomb. Okay, so we've done our magnitude. Now to determine the direction. At point X, the direction would be the direction that a positive charge would go. Our main charge is positive, so our positive charge would go to the right or away from the charge. Okay, and that's it. That's all there is to it. Obviously, they might not ask you to find electric field strength. They could ask you to find the distance away or to find the value of the charge. But either way, it's just a matter of substituting into the formula and solving for whatever your unknown is. Okay, so this is nice and easy. Just one charge Very unlikely you'll get something like this in a test or an exam, maybe as a multiple choice question, but it's a bit too easy for the extended questions. But we're still getting used to it. It's more likely to be something that you'll see tomorrow or the next day. Okay, but make sure that you master using the equation so that when we get to the tricky stuff, you know how it works.